Welcome everyone. I'm Roger Shiverly. I'm going to continue a talk that happened in the previous, discussing some technology from Dieneberg technology. It is the Dieneberg C2S console modeling that we've done. They have a design theory that we were modeling to understand the characteristics and acoustic behavior of it. Previously, Peter Larson talked about a plugin that he has in Finecone to model or to design the architecture. What we've done here is decided to look at the design theory that was put together to explain the acoustics in the patent of the Dieneberg design. And the purpose of the console modeling that we did was to evaluate and analyze that fundamental design theory to see if it had some validity or even compared to the possibility of prototyping. And the reason we went to a model to begin with is because it was very difficult in the beginning for them to do prototyping and to create this design in a way that was realistic. But they have managed to do that. Is what I just noticed that they have one of the speakers up here that I'm talking about. So I'll just set that right there. And so there is a prototype. This happened after we did the modeling, helped them to design this prototype version of it so that they could optimize it for performance. So the idea was that they have what they call a Concentric Coplanar Stabilizer, and I'll describe this a little bit on the next page, because in the patent that Mikhail Dieneberg put together, he described the loudspeaker cone as sort of a diffuser, and I'll just sort of go through this quickly. In terms of a diffuser, he meant something that was creating a boundary that would be an efficient boundary to normalize the sound on both sides of it. And as we know, loudspeakers are somewhat inefficient, and a cone is a very inefficient version of this diffuser. And what he calls that is to make a better match on pressure of the two volumes on the outside and the inside, and he calls that the diffuser. Well, in this case, it's a loudspeaker cone. And what he has in his design is on the outer portion of it, there is the inner portion of the design has an active speaker in the center, and the outer portion of it has what we would call a passive radiator on the periphery. And in this case, if you think of them in terms of a piston, then they are somewhat coplanar, so that's how the name came up with to be coplanar. So in this case, we're calling it the passive ring radiator, but what they're designating that in their description is they call that the stabilizer, or the diffuser, I'm sorry. It's they have two different names for it. I'll go back and get that one up here. So what they've called the outer ring is I'll find it here, is I'm looking for it. I don't see it. The outer ring is the stabilizing part, is what they're simply calling it. So what it is a passive radiator. So what we've done is go ahead and modeled this in console to understand its behavior and see if it has some of the performance parameters that they're looking for. So what I'm about to describe is how we created the model and how we came about to get the results. And the comparison that they wanted to make it to was something that was similar in design, but not with the coplanar or concentric coplanar passive ring radiator, but with a traditional passive radiator. So here is basically the process that you go through with a console model. This is somewhat straightforward in terms of how we go about modeling it. You take what we're seeing here is the CAD model of the loudspeaker. And in the yellow, we have the suspensions. And in the gray, we see the passive membrane, and we see the basket. And then in the white, I'll point to that right here, they have a design, part of their design theory is something called a phase ring. It's meant to control, in theory, from their theory, the relationship between the interactive cone and the passive cone. And this wall here has influence on it, and there is another study that we did to show that there is actually an improvement with the ring, and then you can optimize the design of that ring for the length of it in order to control the interaction between the active cone and the passive cone and improve some of the performance that you'll see later on. So in this case, we created, from the CAD model, we created a simulation model, which is usually somewhat more simplistic, and in this case it is. We've taken the motor and modeled it as a lumped parameter in COMSOL. And so it's a driving force with some BL factor and a DC resistance as well as inductance. And then we have the membrane surface as with a peak driving force that we add in. And from that, the remainder of the modeling components and materials and thickness were defined for paper, cone material, and then glues, paper, cone, surround, spider, air, paper, dust cap and cone, copper, and then for the surrounds it was an NBR rubber surround. So those were actual material properties as opposed to a lumped parameter. So with COMSOL multiphysics, you can either use a lumped parameter model or you can use a full three-dimensional material model. And so in the case of this, it's a magnetic versus added on to a mechanical model, which then gives you acoustic radiation. So we put this into COMSOL, and you can see in this case this is what we have. And again, you can see that here we have the ring that has been meshed and ready to go. The first attempt was done simply to correlate the model to, or calibrate the model to the material. So the first model was done with only the expectation of about 2,000 hertz, and we created it in a free field environment. So if you are familiar with COMSOL, you have the ability to add in a perfectly matched layer. At that point, we are essentially making it a boundary-free, reflective-free boundary, so that you can essentially have a free field radiation. So there's no reflections. And that was the size of this model. It was three-dimensional, and it was a full model of the components. And we did a 12th octave analysis on that just to calibrate the material properties and the performance. We also compared that to a lumped parameter model. And this whole enclosure was about 2.6 liters for the box. And so what we've done is calibrated it, the 3-inch. This is a 3-inch driver, about a 90 millimeter diameter model in the box using an LPM. In this case, the green line is a linear parameter box model, and then the blue line is what was simulated. And we see that we've matched the low frequency. The differences in the mid-range is basically from box loading that we can see that actually exists, that doesn't exist in the linear parameter model, but can be modeled in the COMSOL model in free air. And once we had that, we took and added the Dieneberg alignment, which means we added the outer passive radiator ring to the box. And so now we have it compared to what we had before. And again, we did a base reflex passive radiator as a comparison for the low frequencies, which is the red line here. And the green line, again, is the original 3-inch in a box. The red is a linear parameter model for the low frequencies of a passive radiator in a box, and then the blue line is the actual COMSOL model again. And we can see that we're well matched. This is all on axis, so we're not really seeing any other performance except on axis, and later on we'll see some off axis data, but to do that we had to change the model. So we're basically calibrating our model here to say that we have a good baseline to start analyzing the behavior of this speaker. But like I said, we're on axis, so we don't get to see anything that's off axis. Plus, we're not really seeing a lot of the pressure behavior that's inside the box at those higher frequencies in mid-range. Because one of the things that was understood from some of the early prototypes, which were difficult to measure and correlate to, some of the early prototypes related the sound quality of the alignment to mid-range clarity, and also had a greater improved off-axis behavior. And so in order to do that, we needed to recreate the model for higher frequencies. Oops, let's go back that way. And so to get the off-axis behavior, we had to go up to about 12,000 hertz. So we took a symmetry line, a quarter symmetry line in the model, and recreated the model that way so that we could get up to 12,000 hertz. If we had tried to do that for the full model, it would have been too many elements. We're still in finite element analysis so that we can get a refineness to get the high frequencies, and the element size would have been too small to actually run a model up to 12,000 hertz for the three-dimensional full symmetry. So we went to quarter symmetry on that in order to get it, and then we were able to get up to 12,000 hertz. The mid-range starts to stop working around around 8K, but the was run up to 12 kilohertz. So here we have our basis for our model for looking at the behavior of the Dieneberg alignment in this design. So now we're going to start to look at what's going on. And when we look inside the model, this is again with quarter symmetry. We can see that there's we got a nice refined interior look at so this is a couple of frequencies high up. We can start to see some pretty good behavior here. So what I'll do is take a little bit closer look at what's going on there on the next couple of slides, but we'll look at it from a side view so it's a little easier to see. So what we're seeing is what they described as the phase stabilizing ring here and we'll step through some slides to see what's going on in terms of where the phase null is and where we're changing the mode of phase. But you can see that the phase ring there's some evidence that it has a positive relationship with the active speaker, which is right here, and the passive radiator ring that's here. And so as we go along, we can follow what's going on with these phase lines. This is SPL, but you'll see where the phase changes when you see the lighter color and the pressure in the center that is moving between the active speaker into the passive ring radiator. And so that's what we're going to look at here. So these are lower frequencies, these are mid-range frequencies, about 450 hertz and 600 hertz. When we look at the behavior later on, we're going to still focus on the mid-range and the high frequencies because they seem to have some significance. So here again, this is 450, this is 600. We go up to 800 hertz, and then 1250, and then 1600 hertz. We can start to see the effect of the phase ring here as it affects the higher frequencies. And what it's beginning to do is create somewhat of a cohesive behavior or a relationship between the active speaker and the passive ring radiator, which was the intention of the design theory. As we go above 1600 hertz into 4000, 6000, and 800, we start to see this type of behavior where there may be additional benefits, which we'll show you later in terms of the off-axis behavior. And if we have some time, then we might look at some of the measurements that were made on the box and compare them as well to see what's going on there. So we start to see this, but the idea was to compare it to a standard design, which had the 3-inch in a box this size, but had a passive radiator attached to the box on the rear. So if we look at that, we can see the 3-inch in the center, and the rear of the box now has the ring radiator. And so to look at the comparison between the two is why we did this, so that we could see if a standard alignment of adding a passive radiator to the back of a box had any benefit or any difference between that and the Dieneberg alignment. And so that was the purpose of the next part of this evaluation. And so it was one of the things we wanted to understand is if there was a difference, does it explain why there is a difference between when you listen to that alignment to one that has the passive ring radiator has the passive radiator on the rear. There is a perceived difference in the intelligibility and the clarity, and there seems to be a little bit more depth and detail in the harmony of the vocals, and it seemed when you listen to the Dieneberg one, it tends to have or maintain this behavior when you're far off axis. So we wanted to see if there's any evidence that explained that between the two types of alignments. Instead of just putting a passive radiator on the back, can we do it? Is there a benefit of doing it in line, like the way the Dieneberg is set up? So we'll go ahead and take a look at this model. And the on-axis response, again, we can see here, this is in the black line, we have the Dieneberg one, and in the blue line, we have the rear radiating piston. It's a passive radiator in the rear. So this is, like I said, on axis at about 1 meter out. And we can see that there's some, differences in the behavior, but what's more important is what's happening off axis as well. So on the on axis, there seems to be some benefit. What we'll try to look at is off axis, but before we want to do that, we want to see if there is some differences on the interior that would help explain what's going on inside the box. And here, well, this is a quick animation, so you won't be able to capture any information there until I go to the next slide when we'll go step by step. And we'll go to the next page, and if you remember the previous one, which had the ring here plus the radiator, passive radiator here, we saw some phase interaction between the mid-range between the active speaker and the passive radiator. In this case, we're not seeing any complex behavior here. There's no phase behavior or interaction between the ring of the passive radiator and the 3.5 inch. So it doesn't have to have much complex interior behavior at 450, 600 hertz, and continuing up into the 800 and 1200 and 1600 hertz. We start to see some behavior here at the higher frequencies, but it has no positive benefit to add to the passive radiator behavior or the mid-range behavior. So it's clearly different. Is it a good thing or a bad thing? This is the off-axis response, polar response for the Dieneberg alignment, and then a standard passive radiator, which is on the rear, which we just showed you. And when we look at some of the plots here for frequencies higher than 6,800, you can see that there's a broader off-axis response, meaning we have a little bit less beaming going on here at these higher frequencies as compared to the standard passive radiator. And that continues off to about 660, the angle, off-axis angle about 60 for a lot of the lower upper high frequencies as well. And so there is some improvement in terms of the broadness of the off-axis response that we can see. And so once we look at that, we can say, do we come to a conclusion? So, and we can. And basically what we've done is we've looked at all of these detailed measurements. What we've done is showed that there is some evidence that the arrangement of the coplanar passive ring radiator with the interactive speaker has some performance benefits with or without the phase ring, but the phase ring that was the design ring around the active loudspeakers has an effect that it can be that can control the amount of phase. I mean, between the pressure on both sides of the active and the passive radiator. It can control the phase relationship between the two if we change it. And that's not part of what I'm showing here, but there is a study that we have done to do that as well, which we can publish. And so what we're seeing that there is some benefit for the off-axis up to about 60 degrees. And so a lot of the COMSOL simulations have justified what we're seeing or hearing. So there's now some understanding of the nature of the solution, so now we can apply that to many different things. And one of the benefits of having a passive radiator on the front of your device is you can put it into the ceiling, you can put it into a car door, or you can put it into a set of headphones, and these things are design iterations that are currently being done by Dieneberg. If we have some more time, I'll go through some of the actual physical measurements that were done on this so you can kind of see what it looks like, if that's okay. Let me go ahead and jump into those. Here is a comparison of the Dieneberg alignment versus a prototyped setting up here. showing that there's very much similarity between the simulations plus the prototype that was built. There are some specific changes, differences between them, mostly with the phase ring that was used or capable of being put into the design. Here we can see the power compression is pretty good. It's been able to handle, it's raised, the input is raised for about 3 dB steps. The total level change from start to finish is about 10 dB from 100 to 20K, and there's very minimal compression going on here. Another aspect of the actual realized prototype is that, despite this 10 dB increase, the SPL, the THD from between 500 to 3K went down by as much as 10 dB. In the measurement, the THD levels are, as low as minus 65 dB, which is about 0.05%. In terms of THD. And then also quickly the phase linearity, it was measured, and it made what was, if you look at what was typically called the crossover point around 200 hertz in this type of device, I'm pointing to it right there. There we go. There's a lack of the normal discontinuity that you get when you have a passive radiator, and this could be, at least partially responsible for the Dieneberg alignments, the C2S system's good performance when playing the complex vocal harmonies. One of the things that we did, not only with the realistic prototype, but also with the part in a simulation, in the simulation we could oralize the results, and we could listen to both the passive radiator with the traditional design versus the passive ring radiator, and compare the two, listening on axis and off axis. And to listen to it, you could hear the same thing that was heard when you listened to this device on axis and off axis, that there was a greater clarity in the vocals as you went off axis with this type of alignment versus one that had a traditional passive radiator. And that is one of the things that we were seeing, that the off-axis was stable and it had less distortion off-axis as well. And with the phase linearity, that somewhat explains why that was going to happen, because you didn't have any discontinuities in the phase relationship. And then if you look at group delay, which is also measured on this device, is that it's, what we're looking for is a very smooth, constant delay over a wide frequency range. And so from the low frequencies that are typically reproduced by the woofer up to the frequency reproduced by the tweeter, it should vary very slightly, and the measurements here show that from 400 to 10K, the group delay was plus or minus 250 milliseconds, which is indeed very light and slight and smooth. So in a sense, we see that there's a lot of evidence that there's some value to the design theory that was put together. The simulations work that we did helped produce this design, because there was no way to design the ring and the components of the loudspeaker until we could actually simulate them and then produce that prototype. And so from here on, we now can iterate it to produce it for different applications, like I say, for ceilings or for doors, or for even smaller setups for headphones. This could also go on a wall, and it could be scaled up in terms of size. And there seems to be a very good evidence that there is a good capability for producing off-axis and reduced harmonic distortion, which adds to the clarity and the richness of the vocals. So that's a good chance that every application will have the same behavior as well. And that's mostly what we had. I can take some questions on any part of it, and if anybody has some questions, I'd love to hear them and give you some feedback. Yes?
With that phase ring, was it a function of the height of it or the diameter, or was it that change?
It was a function of the height mostly, and then that's also constrained by the depth of what you're dealing with. So, but you could make it wider. If you ran out of depth, you could make it wider and sort of compensate as well. So it's just a matter of finding the optimal width and height of it to create a positive interaction. So what happened when we took it away, I don't have the data here, but when we took away the phase ring, we started having less broadness of the off-axis behavior, so it started to improve. When you put the ring back in, you could see that it was actually changing the high frequencies, like in this range of from 1200 to 1600 hertz. It started to change the off-axis behavior. And it also changed the phase linearity, and it changed all the phase relationships inside the box. And it had a direct correlation to the listening experiences that we're having. So, yeah. Yes, but not too much, because there was a point where what we tried to do is, part of the simulation was how small of a box can you use. So we had started with a much larger box and a much larger design, so we optimized it down to a 3-inch. The first one was a 6-inch active speaker with a 12-inch passive, and a larger box of about 20 liters. And then we just started to scale it down to something that could be using a 6-inch mounting, a 6-inch mounting with a 3-inch center. And then it was a question of finding how slim could you make the box. And so and it came out to be 2.64 liters based on the depth. And so that was where we started having too much interference and poor behavior with the back wall. And that turns out to be a good depth for most of its applications. If it's an overhead speaker or a wall speaker, even this fits into the door of a car. And then when you scale that down, you can go through the same process for a headphone or wherever you might. And also you can go to larger diameters. Because we did start at larger because that was the application they were thinking of. But they wanted to see if they could optimize it for something that was somewhat common, which was a 6-inch. So 6-inch mounting, that is. Yeah. And the other aspect I didn't talk about, which was somewhat related to the measurements that were done, is that with the passive radiator, they were obviously helping the 3-inch. Now the 3-inch can take with the THD measurements that we saw, it can take a higher power input and still not have the distortion that you would typically associate with that in a 3-inch diameter loudspeaker. It's capable of producing more low frequencies without having to be as much excursion, and so it stayed linear for a greater power level. So, which we weren't sure was going to be possible, because intuitively you think you're going to have problems no matter what, but with the ring, it seemed to stabilize everything. A passive radiator can do that, but this one being on the front of the box and more or less in the same plane as the 3-inch had an improvement that is exactly as explained and as theorized by McHale. So, okay. Oh. Thank you for your time. Thank you for your attention. Appreciate it.